So sorry about that. All right, this is the same kind of business. It goes through an aldehyde. H dot dot minus attacks. T of the aldehyde. Details later because it's again kind of a topic of a future chapter. You'll learn it. And then same business, aldehyde, alcohol. H minus attacks, then you protonate. That's all there is to it. That's, so these are great ways to make alcohols from ketones, aldehydes, acids, and esters. Great ways to make alcohols. Okay, so I'm going to say real quickly, this is a stronger, more reactive, than NABH4. It's stronger, more reactive, and it's actually much more dangerous too. It's very easy to almost burn down your lab with this stuff. So you have to be very careful with lithium aluminum hydride. Sodium borohydride is not that bad. The other one, and actually in the lab, in the teaching lab for 336, you guys use sodium borohydride next week. Actually, you do an NABH4 reaction. Lithium aluminum hydride is not one we do in the teaching lab because it's very easy to catch the lab on fire. Okay, so with good training, you know. Like in a PhD program, you would routinely use lithium aluminum hydride. Sodium borohydride is something that we can even do pretty easily with pretty minimal training and expertise. It's not as flammable. Okay, that's cool. All right, so then the obvious question is, why do we need a stronger reducing agent for esters and esters and acids? That's a good question, right? Why do we need this stronger reducing agent? Why can't we use sodium borohydride? Any ideas? Yeah, something like that. Exactly. It's more stable. If something is more stable, you need a bigger hammer. All right. So why do we need a stronger H minus source? The basic reason is esters have additional stability. By what mechanism? Imply something? So the oxygen in the ester can take electrons in and resonate. This is a stabilizing interaction, right? Same with acids. Stabilizing interactions. When something's stable, you need a more reactive reagent, and thus lithium aluminum hydride. Okay. Okay, so this is an example, and I mentioned this in passing about the fire hazard of lithium aluminum hydride. So, just as an example, say I have, here, let's think about this one. I got a ketone. Ketones will work with lithium aluminum hydride to reduce. Okay, ketones will react with this lithium aluminum hydride. They will. Of course they will. I mean, it's a bigger hammer. It's going to do that reduction, no problem. Okay, no problem. I'm just going to pretend, oh, whoops, we used methanol, just to see what happens, okay? And it should be okay, whatever. Okay, so what would happen if you use lithium aluminum hydride in the presence of methanol? Let me see, I have my, oh, I'm going to try to draw a fire with my marker. But how does the fire ensue? It's this way. So rather than your H minus being a nice nucleophile, your H minus is going to act as a base here. And you're just going to see this methanol. It's going to see the methanol, and it's going to take that proton. Because the proton in methanol is kind of acidic. So what happens when H minus grabs an H from methanol? You make what? H minus plus H plus H2 plus heat. H2 plus heat makes fire. Lots of fire. You make a lot of H2. You make a lot of heat. And in the case of I didn't make this mistake, but it was a pretty complex situation. Huge fireball in my research lab, and as a grad student, I wasn't faculty. But like, as in, huge fireball, everything burnable is burning. So all the power cords, all the little rubber tubing, everything's burning, right? So that was kind of freaky. It put itself out, though. It was very fast. And before, I don't know, it's a long story. Rather than call the fire department, it was out in 5 minutes or something like that. So lithium aluminum hydride is dangerous stuff. You got to be careful with it and be more properly trained than I was, in fact. Okay, so lithium aluminum hydride plus methanol is bad. Why is lithium aluminum hydride plus ether okay? What's the difference between methanol and ether? Or alcohol and ether? Any acidic protons? No acidic protons. Good inert solvent. Good inert solvent. And when you have a good inert solvent, you don't have to worry about this H2 business and the ensuing fireball. Okay? So inert. Ether is a great inert solvent. Any other inert solvents kind of like ether? Anybody know? THF. THF is another one. Very good general purpose solvent. THF is also used for these reactions. It's called tetrahydrofuran. Tetrahydrofuran is a kind of default solvent for a lot of reactions. Yeah, so that's the other one that people use with lithium aluminum hydride. All right. One other thing. This is sometimes abbreviated LAH. LAH is another abbreviation for lithium aluminum hydride. Okay. All right. Cool. I think the book mentioned some biochemistry examples. You can read them, but it's not part of my course, so it's kind of just optional. I would recommend reading it. It's just pretty much don't worry about anything that's in the book that I don't talk about being on the test, all right? So that's a general statement, all right? If it's something completely different that's in the book, you can read it, but don't worry about it being a testable idea. And the biochemistry examples in general are something we're going to skip just due to lack of time, except at the very end when we actually talk about biochemistry. Okay, great. Let's see. All right, so that was lithium aluminum hydride and sodium borohydride. What's a good abbreviation for those? Well, we can say nucleophilic H minuses. Nucleophilic H minus sources. That's what those are. All right, nucleophilic H minus. So, next one. separation of alcohols with a Grignard reagent. Definitely a nice big star there to suggest this is one of the most important things you will learn in organic chemistry too. And good thing you're not skipping today, because this is definitely something you're going to see from here till the very end of the semester a bunch. You actually have seen Grignard. Anybody remember that word? Organic one. It was one of these things that was mentioned in passing as kind of like a really cool thing, but we're not going to tell you about it until later. Well, that was later. So this is the whole time to learn about Grignards, and it's a very important CC bond forming reaction. CC bond forming reaction. CC bond forming reactions are, to me, the coolest reactions in organic chemistry, because you can start building things. It's like Legos, right? You can build your complicated molecules with CC bond forming reactions. All right, so let's see. Making a Grignard. Let's review. Rx, magnesium, usually ether or THF in there. What does Grignard look like? RMGX. X is a halogen. X is usually Cl, Br, etc. So chlorine, bromine, sometimes iodine even. Okay? And it makes this thing where the magnesium kind of sneaks in between the atoms. Okay? And this is equivalent to R dot dot minus nucleophilic, which is going to guide its reactivity. Okay, so nucleophilic R dot dot minus. Nucleophilic R dot dot minus, right? Okay, example, ethyl bromide, magnesium, THF. Ethyl bromide, or bromomethane. Magnesium, I use THF there. THF ether, you know, these inert solvents are really good for this kind of stuff. And basically, this is what it's kind of equivalent to. It's 2 carbons with a negative charge on it, right? Is this a nice happy reagent? No, no. Very unhappy, very reactive. Why? Why is this so reactive? Minus a carbon, yeah. Carbon's not electronegative. So you put a negative charge on carbon, it's not very happy, right? And it really wants to get rid of that negative charge by either being a nucleophile or a base. So this is going to be nucleophilic, and it's also basic. Nucleophilic. We're going to use it nucleophilically, but it is also basic. So, meaning that if you have an acidic proton around, it's going to be destroyed. Okay. Carbon with a negative charge is immensely reactive. All right. Cool. So, examples. Oh yeah, how do you make a bromide? Say we have an alcohol. We'll make bromide. PBr3. Of course, say we have a bunch of acetaldehyde, and the world ethanol supply just evaporated. But we have acetaldehyde. How do we make an alcohol from acetaldehyde? NADH. Unlikely that world ethanol supply will dry up by tomorrow, but yeah, I'm mostly trying to review these reactions with you, right? This is a theoretical exercise. Okay. nobody in their right mind would generate ethanol by this reaction, because you can buy ethanol by the 20-liter can for 15 bucks, you know, so. But I do want to review these reactions as much as I can to keep them stuck in your mind. All right, so using a Grignard, you know how to make them? Let's use them now. Propyl Grignard, and you do H3O as second step. Usually for solvent, THF or ether, parentheses, okay. Nice inert solvent, but don't worry about memorizing solvent choice. Okay, and what's going to happen is we're going to get an alcohol out now. An alcohol with how many extra carbons? So the carbon, we have nucleophilic carbon. That's cool. Nucleophilic carbon. Just like a second ago, we had nucleophilic hydrogen. Nucleophilic hydrogen, nucleophilic carbon. We can start doing some cool stuff. All right, so mechanism-wise, there's a 3-carbon piece. All right. Is the same as this. So this is the same as, you know, this is an acceptable nomenclature for that 3-carbon piece with a negative charge. It's propyl ... negative, 3 carbons, ... negative. What's it going to do to my ketone? Nucleophilic? That is. Okay. Why do I do this CH2 ... negative? I'm just trying, you know, usually I skip hydrogens. Here I want to make it clear how many hydrogens we have, and also just make it clear that we have a ... negative. So that's kind of why I do this. I sort of did the same thing here. You know, I hate this kind of nomenclature in general, but with a Grignard and then like a negative charge, I think it's nice and it makes it clear. More clear to me than saying like that, right? I think that would be the alternative way we could say that, but that's kind of, this is a case where the line bond, you know, staggered skeletal structure format is kind of limited, right? I'd rather say this. This is very clear. CH3, CH2, ... negative. Okay. All right. But here, you know, these are acceptable ways to draw this Grignard. Here we can see what happens. What do we get out? Brackets. Okay. What do we get? The propyl attacks. We get an intermediate. What do I call these things? Oxygen with negative charge is not an alcohol, but a alkoxide. Alkoxide, all right? What do you think the counterion is on that O minus? Obviously there's something to balance the charge. MgBr plus. MgBr plus. It's just a counterion, doesn't do anything, but it's definitely there. Okay? Cool. You can do it on ketones, you can do it on aldehydes.
Quick question, so
Yeah.
you get the alcohol's proton from,
H3O.
yeah.
Yeah, sorry. H3O. Mechanism is O minus attacks, H plus. And then you get probably